Hello, Internet. Today, one of the most fascinating topics in learning on graphs, it is representation learning on graphs. And as you can see, I have here a document from our arXiv servers, arXiv 1709-05584 version 3. So let's jump right into it. You know that machine learning on graph is not a trivial topic. And I want to show you here documentation from April 2018, where they talk about how to encode a graph structure so that it can be easily exploited by machine learning models. So before you start with your machine learning, you have a graph structure, and the presentation of this graph is not optimal. And you want to try to present the optimal version of your data set before you start your machine learning exercise. And they say that to automatically learn how to encode a graph structure into a low-dimensional embedding. And this is important because the graph can, at first, there is a non-Euclidean structure, the topology, and it can have some really high dimensionality. So if you want to reduce the complexity of the graph, you can try to encode the information in the graph and the graph structure. So the information in the nodes, in the weights, all the edges, the connectivity, the topological structure, the complexity of the graph, you can try to reduce this to a lower dimensional space. Would be ideal if you could have it at a low-dimensional vector space that you can calculate the embeddings of the nodes of the graph and everything of the graph. So you want to have a low-dimensional embedding to then feed this reduced data set to your machine learning exercise to have a very fast calculation on the models. And here they have this overview, this conceptual review of key advancement in the area of representation learning on graph. And these include matrix factorization-based methods, the random walk-based algorithms we already know, and graph convolution network I showed you already with Thomas Kipf. So let's start right into it, and you will see it is really, really important to understand representational learning of a data structure with a graph, because then we can find some machine learning algorithms that are really fast and really efficient. So here we go. Of course, their aim is we want to make prediction, discover new pattern using graph structure data as feature information, as input information. And they give you here an example that you have here, for example, I don't know, this is from Les Miserables, the novel, and the players, and you see here all the players in green, they come from, I don't know, the upper east side, and the players in blue come from the lower east side, and the players in red come from the upper north side, and you know, I'm a professional geographic expert in New York City location. So, but what is interesting that you have here community structure defined by the structure, by the classes of the community, but you can have some structural presentation. And this here on the right hand side is done by node-to-vec embedding method, and I will show this in a second. So the central problem in machine learning on graphs is a way to incorporate the information about the structure of the graph into the machine learning models. And the question is how to do this. And this is the idea behind representation learning, is to learn a mapping that embeds the nodes or entire graphs or subgraphs as points in a low-dimensional topological space, and we hope to have a vector space. So the goal is to optimize this mapping so that the geometric relationship in this learned low-dimensional space reflect the structure of the graph, the node, the edges of the original graph. So the structure of the original graph is encoded in a lower dimensional representation, and this is why the name is representational learning. And after optimizing the embedded space, so the new space that we encoded our information, The learned embeddings can then be used as feature input to downstream machine learning tasks. And you are familiar with feature inputs like, say, in word embeddings or in sentence embeddings, SBERT, because this is exactly what we have done as the data pipeline for graph neural networks computation. So the representation learning approaches as a machine learning task in itself. Yes, we understand this. And here we have now an example. And this is the famous Karate Club social network, where you have here on A, on the left side, you have here a graph. You can have this in a three-dimensional representation. And we remember we have no Euclidean metric behind this. There's no notion of distance. If you have a relationship between node A and node B, it doesn't tell you anything about the distance. The question is, how do you define the metric of a space, how you define closeness between the nodes, and how you embed these nodes? And this is the main topic of this presentation, and they present it very nicely here in this paper. So here we go. The nodes are colored according to different communities and exist in the network here. And then we come here from a higher dimensional non-Euclidean presentation, and we want to get a two-dimensional, a very simple two-dimensional representation, where we have now that the distances between the nodes in this embedded space, and this is our embedded space, reflect the proximity on the original graph. So you can see here, since we have a color encoded node 17 to node 6, we have node 17 to node 6, and we can say, yeah, they are about in a local epsilon environment, or in a local, no, not too much topology, in a local environment, and they are close by if you want. And of course, the problem is to define it in a mathematical, sensible way that we can really deploy some code on this, and we can calculate, automate it before we use this representation of the graph data. B will be the input to our neural network calculations, because as you can see, it's much easier. It's on a two-dimensional grid, and this is a simple exercise. So this is representational learning, a lower dimensional embedded space, where we have node embeddings, where we have that the vicinity of the nodes and the closeness of the nodes of the graph is taken care of and represented in this embedded presentation. So we have, of course, for the graph, we have an adjacency matrix, and we have a matrix that represents all our node attributes, and the adjacency matrix is denoted A. Our matrix of node attributes is X, and we can map each node, a subgraph, now to a vector Z in our embedded space. And here we go again. Of course, the models we can use here to embed our nodes. You are familiar where the goal is to encode nodes as a low-dimensional vector that summarizes their graph position. This is it. And the structure of the local graph neighborhood. Of course, we want to have the graph information and the structural information of the graph encoded. And one of these is, of course, an encoder-decoder perspective. You know this maybe from vision neural network, where you have multiple encoder-decoder arrays. But now here we apply the same idea, and we have an encoder which maps each node to a lower dimensional vector, or our embedding in our embedded space, and a decoder which decodes the structural information about our original graph from the learned embeddings. And the intuition is that this embedding should contain all information necessary for the next machine learning task, so we can use a simpler, less complex representation of our data, of our input data. And you can define the encoder function and the decoder function, and of course this is a pairwise decoder. And if you want to have a look at this in a schema, you see you have here your input graph, and you have a node, and you want to find a representation in the embedding space that looks like this. Set the vectors. We have an Euclidean matrix. We can do some cosine similarity calculation in the trivial case. And we have now multiple steps. So we encode all the nodes, and then we have with the encode, and then we have our decoder on the right-hand part, where we decode the information about the neighborhood, and we could decode the node label, the label-specific information. And after run do this, and you define a loss function, and you optimize the system, and at a certain step in time, you find that the precision in the embedding the vectors which encode the nodes is good enough that you can say this representation of the graph here in our embedded space is equivalent to the structural information of the graph, and we can use it as input data for our neural networks. Yeah, you can go, of course, some very simple notation. We apply pairwise decoder to a pair of embeddings, and we gain a reconstruction of the proximity between Vi and Vj in the original graph. And the goal is to optimize the encoder and decoder mappings to minimize the loss. And you can find the loss, and we see here the empirical loss is defined simply here. And we have now an optimized encoder-decoder system, which used the trained encoder to generate embeddings for nodes, which can then be used as feature inputs for downstream machine learning tasks. This is it. So we have a pairwise proximity function defined over the graph. This measures how closely connected our nearby measure, if you want, two nodes are in the graph. We have an encoder function, we have a decoder function, we have a loss function, and this enables the system to train, to apply learning functions, aggregation functions to optimize the embedding representation of the graph structure, of the data that have a graph structure. Of course, you can use stochastic gradient descent for optimization. You are familiar with this. We do not have to go into this. Now, as I told you, there are different methods. We have some Laplacian eigenmaps. We have some inner product methods. And what is a nice one is a random walk. And let's have very short a random walk presentation. This is the class of direct encoding approaches, and they learn the node embeddings based on some random walk statistics. The key innovation is optimizing the node embeddings so that the nodes have similar embeddings if they tend to occur on a short random walk, a defined length of random walk over the graph. So instead of using a deterministic measure of graph proximity, these random walk methods employ a flexible stochastic measure of graph proximity, which has led to a superior performance in a number of settings. So in the time, you remember this is a documentation, a publication of 2018. They found that random walk are not so bad. We will learn that it has some disadvantages, but for the moment being, let's have a look at this. And the idea behind random walk is quite simple, and it's beautifully presented here in this graph. The random walk-based methods samples a large number, a stream of fixed length random walks starting from each node Vi, and the embeddings vector are optimized so that the dot product, so in a vector space, topological space, we have a dot product, we have a metric defined. So the angle between the vectors of two embeddings, set I and set j, is roughly proportional to the probability of visiting the node Vj on a fixed length random walk starting from Vi. So we have here on our graph structure, on our non-Euclidean graph structure, we have a set of fixed length random walks from one node to the other, and the probability that on one of those streams of these walks you have the node Vi and you visit the node Vj, this probability is equivalent to the co-occurrence statistics when you calculate in a vector space the embedding of those nodes. So this is the main idea behind this. Equivalent probability densities on the graph structure correspond to a correspondent equivalent closeness in a vector space calculated, for example, with a dot product or whatever. This was the random walk approach. Yes, you can now have about close in your, based on the symmetry of your data, close in your vicinity, or you go deeper into the network. Based on this, you have variations. But what I want to show you, deep walk and node to WEC, they rely on direct encoding and use a decoder based on the inner product. However, instead of trying with some deterministic method, we have this already. Our loss function is the cross entropy loss. It is defined here. Deep walk implies a hierarchical softmax technique to compute a normalization factor. And node to WEC approximate this with negative sampling. Negative sampling, you're familiar with. If you calculate some word embeddings, you know exactly what negative sampling is and how it optimizes and accelerates our computing time. So what is next? Yes, of course, there is the next step of improvement. You have large-scale information networks embedding line is to be mentioned. You have a first order and second order graph proximity. You have a 2-hop adjacency neighborhood. You can optimize this. This is, yeah. What is the drawback? The number of drawbacks of all of these methods that lead to the development of a new method, graph search, and no parameters are shared between the nodes in the encoder. So more or less, the encoder is simply an embedding lookup based on the node IDs. Direct encoding also fails to leverage node attributes during encoding, and they are inherently transductive. They only can generate embeddings for the nodes that are present, and they cannot generate embeddings for unseen nodes, from previously unseen nodes when you did the optimization of the embedding representation. So you have, every time you add a node, you add a link, you have to do the whole embedding again. And now you have some deep neural graph representation and structural deep neural graph embeddings, so DNGR and SDNE. And they address the first problem. So you see step by step, we develop models and methodologies to solve here the limitations to increase our product. Of course, instead of a simple network, you have now a deep autoencoder where the principle is the same. You have your graph, you have your embedding, but you run through some deep autoencoding. They say here the neighborhood autoencoder approaches first extract a high-dimensional neighborhood vector which summarizes the proximity of our node Vi to all other nodes in the graph, and then the embedded vector is then fed through a deep autoencoder. You reduce its dimensionality. We notice producing a low-dimensional SI embedding. So you see just a deep autoencoder. We have a similar understanding what's going on. And then the neighborhood aggregation, and this is where we come into our message passing. We find the path to our message passing structure by GNNs, but let's go step by step. And wait, I think I have, let me have a look. I think we have here an update presentation on graph 7, presentation 7. Where is it? Where is it? Where is it? Come on. Sorry, behind the scene, I'm searching for a presentation. So here it is. Yes, this is figure 9, figure 7 now. A little bit more interesting. Oops. Just a second, some problems here. Uh-oh, yes, this was the wrong. Here we go. Here we go. So you can see here the overview of encoding in a neighborhood aggregation methodology. And you can find the same visualization if you have a look at Stanford Online. I'll leave you a link for this very good, very excellent course from Stanford on graph neural networks. And to generate an embedding for node A, the model aggregates messages from a local neighborhood. And for A, of course, this is the node B and the node D. And then C, green, of course. And in turn, the message comes from these neighborhoods are based on information aggregated from their neighborhoods. So it goes on and on and on and on. Great. So we can cancel this. We have a look at the old presentation where you have the neighborhood aggregation method now. To generate an embedding for the node, the method first collects the node's k-hop neighborhood, so k equal 1, k equal 2, so you know this n-hop neighborhood. In the next step, they aggregate the attributes of the node's neighbor using neural node aggregators, and this aggregated neighborhood information is used to generate an embedding, which is then fed to the decoder. So again, we are looking to have an embedding of all the structural and the node information of our graph or of our subgraph. And the way to do this, this encoding, yes, encoding, you can optimize it step by step by step. And yeah, we know already the convolutional method by Thomas Kipfer. I showed you this in another video. And the neighborhood aggregation encoder algorithm is this one. And you will find a structural similarity if you then look at the message passing. So this is it. Yeah, and of course, there are a number of recent approaches that follow the basic procedures outlined in algorithm 1. We just had a look at this, including graph convolution network. I had a video on this. Column network. No, I did not show you this one. And the graph sage algorithm. How to aggregate information from a node's local neighborhood. This is the main question, and we have seen there are some different approaches to this. In principle, graph sage, column network, and GCN encoders can be combined with any of the previous discussed decoders and encoders, and loss function and our system can then be optimized using stochastic gradient descent. Yes, of course. Kip used a decoder and a loss function similar to graph factorization approach. You can play around with all the different parameters. You combine them. This is, of course, multimodal graphs. This is it. No, we don't have to look at this. So I think this is a very, very nice presentation. Let's go back to the very beginning where we have, I think here we go, encoder and decoder, where we have a complex graph structure, non-Euclidean structure, and we encode it in a vector space where all the nodes have get a vector, and depending on the attributes of the node and the vicinity of the node and the n-dimensional k-hops of the graph structure, you can optimize an embedding, a low-dimensional vector space embedding that present a better representation of your data that are structured in this complex non-Euclidean graph structure. You have a beautiful vector space where you can operate with the methodology you are familiar with from your visual neural networks and your other approaches to topological spaces and dimensionality reduction of topological spaces. I think this is it for today. I'll leave you to a link to this publication. I can really recommend it. You get some deep insights into the node embedding structure plus the graph structure. So representation learning on graphs, methods and application from 2018. Although it is an old publication, you'll learn a lot of it. I did learn a lot of it, and I'll see you in the next video.